Helen's 45-year journey from the 1980 eruption's devastation to astonishing ecological rebirth, seismic mysteries, and new scientific warnings. What secrets still stir beneath this restless giant? And could its next chapter reshape our understanding of Earth's power and resilience? Don't look away, because what's unfolding at Mount St. Helens may change how we see the planet itself. Volcanologists will tell you to this day that St. Helens remains the most active volcano in our state. High in the shadowy heart of the Cascade Range, a mountain once stood cloaked in timeless forest and a deceptive calm. For centuries, Mount St. Helens slumbered, its looming silhouette mirrored on the surface of Coldwater Lake, its slopes traced by rivers and ancient trails. The local indigenous peoples believed the peak was inhabited by a restless spirit, while to countless visitors, it was a striking backdrop to Washington's wild frontier. All that changed on the morning of May 18, 1980, when one of North America's most devastating natural disasters shattered the calm, unleashing a force that would forever alter the region and the science of volcanology. The eruption of Mount St. Helens, now marking its 45th anniversary in 2025, is etched into collective memory by images of a collapsing summit, an earth-shaking lateral blast, and plumes of ash cloaking skies from Washington to Oklahoma. In minutes, the mountain lost 1,300 feet of elevation. Vast forests were obliterated, rivers were dammed by mud flows, and 57 lives were tragically lost. Out of this catastrophe, a new era of scientific discovery emerged as geologists, biologists, and ecologists converged on the transformed landscape, determined to unravel daunting questions. What secrets lay hidden beneath the ash and debris? How does wounded Earth heal itself? And what can its renewal teach us about life's resilience and the power of our dynamic planet? As the Mount St. Helens Science and Learning Center welcomes a new season of visitors and researchers, the story of this mountain is more urgent than ever. Today, federal budget cuts threaten the very programs dedicated to its stewardship and public safety, even as the volcano remains the most active in the contiguous United States. A sobering reminder that its story continues. What has 45 years of observation and research revealed about the mountain's inner workings? And what mysteries remain? What discoveries lie in wait amid its regenerated meadows and barren slopes? Join us as we explore the ongoing saga of Mount St. Helens, a monument to destruction and rebirth, a living laboratory, and a keeper of secrets yet to be unveiled. How did the disaster of 1980 spark a relentless quest for knowledge? And what may still be hidden in the shadow of this restless giant? A catastrophe etched in time. It was an early Sunday morning on May 18, 1980. The air was crisp in the valley below Mount St. Helens was shrouded in an uneasy stillness. Scientists monitoring the volcano had long issued warnings. After weeks of tremors, minor explosions, and a noticeable bulge growing on the north flank, yet nothing could prepare anyone for what happened next. At 8:32 a.m., a magnitude 5.1 earthquake struck beneath the volcano's northern slope. Within seconds, the entire flank collapsed, triggering the largest terrestrial landslide ever recorded. This landslide rapidly uncorked pressurized gas and magma within the volcano, unleashing a lateral blast that swept through the northern landscape at over 300 miles per hour. Superheated ash, gas, and rock roared across dozens of miles. Forests were shredded, river valleys filled with debris, and ash darkened the sky as a towering plume rose more than 80,000 feet, dusting 11 states. The devastation was staggering. More than 200 square miles of forest fell before the blast. Spirit Lake, once tranquil and popular with outdoor enthusiasts, was smothered beneath debris and log rafts. Its waters, ecosystem, and surrounding land were transformed overnight. Pyrolastic flows raced down the slopes, erasing all life in their path within minutes. In total, the human toll stood at 57. Scientists, loggers, photographers, and residents caught by the mountain's fury. Out of this destruction came a unique opportunity. The Mount St. Helens National Volcanic Monument was established soon after the eruption, preserving the blast zone as a living laboratory, where every disturbance and every step of ecological renewal would be monitored. Here, the drama of death and life played out in scale and detail never seen before, and the volatile forces shaping our planet could be tracked as they unfolded. The eruption also upended established thinking among geologists. The incredible destructiveness of the lateral blast. The force, speed, and scope forced the scientific community to rethink assumptions that the main hazards from eruptions always originate from a volcano summit. Mount St. Helens became not just a site of disaster, but the catalyst for modern volcanic hazard research. What would scientists find when they dared to enter the heart of disaster's aftermath? Could life ever return to a land so thoroughly scoured? Land of ash and opportunity. The science of recovery. To a casual observer, the post-eruption landscape might have seemed utterly barren. An ash-covered wasteland stripped bare by fire and heat. But nature proved more resilient and inventive than expected. Ecologists, assuming decades would pass before life returned, instead found the slow pulse of recovery beating almost immediately after the eruption. Just months after the blast, the first green shoots pierced the grey ash, willow, fireweed, and especially prairie lupine. The purple flower, by fixing nitrogen in the impoverished soil, paved the way for other plant species. The return of life wasn't always orderly. Its story was shaped by chance, available seed banks, and landforms that accidentally protected certain areas from the worst devastation. In lakes formed by blocked streams, amphibian eggs appeared where hot mud had rushed only weeks earlier. Scientists meticulously tracked the process of ecological succession. They monitored the reappearance of microbes in once sterile soils, watched insects colonize, and observed rodents, some shielded in burrows, emerging to gather seeds and aerate the ground. Carefully fenced plots compared recovery in areas with and without browsing by elk and deer, revealing how herbivores shaped the return of forests and meadows. Spirit Lake, among the blast's most conspicuous victims, became a symbol of nature's resourcefulness. Initially blanketed by floating logs and heavy debris, and plagued by dramatic chemical changes, the lake turned anoxic and seemingly lifeless, but new forms of bacteria flourished in these extreme conditions, generating gases and breaking down organic matter. Over the following years, as nutrients filtered in and oxygen was gradually restored, the lake hosted an explosion of algae and later zooplankton, spawning a new aquatic ecosystem, unlike the one lost in 1980. What continues to surprise ecologists is the unpredictability and rapidity of recovery. Each patch of ground, each pocket of shelter became a miniature experiment in adaptation and survival. The process inspired new thinking about post-disaster recovery worldwide. From wildfire landscapes to volcanoes on other continents, the resilient scene at Mount St. Helens, studied for decades, continues to inform science about species survival strategies and the dynamics of communities reshaping after catastrophic change. Inside the volcano. Probing Mount St. Helens' hidden engine. If the 1980 blast revealed the volcano's destructive power, it also triggered an unprecedented campaign to understand what stirs beneath its surface. Mount St. Helens has remained the most active volcano in the lower 48 states. A distinction grounded in its frequent eruptions, dome growth, and persistent seismic activity over the past 4.5 decades. In the years following 1980, dome-building eruptions occurred with remarkable regularity. Each event providing insights into the mountain's internal plumbing. Thick, viscous lava slowly heaped up within the crater, solidifying into spiny towers. A process watched by geologists with both awe and scientific urgency. Central to these observations was the deployment of a vast range of monitoring equipment, seismometers to detect earthquakes, GPS and tilt meters to measure ground deformation, gas sensors to track emissions like sulfur dioxide, and thermal cameras to spot hot spots and steam vents on the flanks. Each tool captured pieces of a complex, ever-changing picture of magmatic activity deep underground. Volcanologists learned quickly that each earthquake, spike in gas release, or ground tremor could precage further eruptions or simply mark the volcano's ongoing restlessness without leading to another catastrophic event. New technologies such as satellite-based radar,